Good morning. So we are going to continue talking about the acceleration and then do a force balance for deriving the famous Bernoulli equation. And today, after we do the Bernoulli equation, we are going to do an example. I want you to do that on a sheet of paper, put your name and hand it back to me as participation exercise. Just an easy way for you to earn 1% credit just by participating. If you want, you can take a picture of your work so that you can use it for study. Okay. Just take a sheet and pass it. Take one sheet and pass it. Have you guys started working out problems on chapter 2? If you haven't started yet, that's not good. Please start. But I see some heads nodding. That's a good sign. Okay. And so far, nobody from this course has come to my office hours. Do you guys know when my office hours are? It is posted on the syllabus. Do you know that? Do you know that I have office hours? Do you know the times? Tuesday, Thursdays, 1:30 to 2:20, and Friday, 12 to 1. If I'm having any schedule conflicts, I'll announce it by email. Like this week, I may not be able to make the 12 to 1, but I'll provide an alternate time on Friday. But so far, I have had 0 visitors. Either that means you don't want to talk to me outside of, unless you have to deal with me in class, or you just get everything and there's nothing to talk. I think it's the first one. So please come to office hour. Please do some problems. Get stuck. Let me help you. Let's talk. Let's discuss. Okay. I hope you'll come through. Are you using the YouTube videos? Is it helping you watch later to learn? Is it helping? Yes. Okay. Thank you. If you have any feedback on how to make those more useful, in the sense, if something is not clear, please let me know. Okay. I'll try to fix it. Audio quality, my speed, talking, whatever. Okay. So last lecture, we talked about how when a fluid is going along a streamline, the speed is the rate of change of position along the streamline or along a path where the fluid is traveling. And we also talked about acceleration. So we recognize that when you have a fluid fluid flowing along the streamline, the velocity has to be along the tangent. That's the first thing we reason. If it's not along the tangent, then you're not following that streamline. So by definition, it has to be along the path of the streamline. And even if that is the case, the acceleration along the of the fluid can be arbitrary, because the force that is causing it need not be along the streamline, which means the acceleration, whatever its direction, it can be resolved into a streamwise component and a normal component. We wrote out expressions for both of them as a function of the local velocity and the local radius of curvature. Do you remember this, recalling this? That we talked about what is the streamwise acceleration, which I told you can be remembered as the rate of change of the quantity v squared over 2 along the streamline. So this is the English translation. The streamwise component is the rate of change of the quantity v squared over 2 along the streamline. The normal component of the acceleration is given by the local velocity squared divided by the local radius of curvature at that point. Okay, so now we are going to use this acceleration to derive the Bernoulli equation. Are you with me so far? Anybody has questions from last lecture? Okay. So this is a figure from the textbook. Let me make this bigger and more readable. Okay. The derivation itself is quite laborious. I'm not going to go through the derivation, nor am I going to ask you to do the derivation in the exam. But I want to tell you what the gist of the story is and skip ahead to the final expression. Okay. Now think of a fluid flow situation where you have a streamline and you take an arbitrary point. This is where the story begins. An arbitrary point, a little parcel or a fluid particle, and we are going to look at do a force balance on that little particle. Okay, see so far, all right. So that little dot I put here, okay, imagine that is a very teeny tiny amount of fluid with still enough molecules that you can call it a fluid, and we are going to do a force balance on that tiny fluid particle. Then, if that is the case, what I draw as a colored dot here, the magnified version of that is this figure. So along the streamline, I identify a fluid particle. It has a certain volume. Let's say its sides are given by delta S, the distance measured along the streamline, and delta N, the distance measured perpendicular to the streamline. With me, this is the square, rectangle. It has two sides, delta S and delta N. Delta S being the side along the streamline, delta N being the side measured perpendicular to the streamline. Yes? Oh, yeah, sorry? I'm just oh, okay, sorry. I thought you were going to ask. Sorry. Okay, so we are taking a fluid element whose shape is like a little rectangle. And you can think of it as a little cuboid or a pillbox, except the third dimension comes along the plane of the paper or outside the plane of the paper. We don't have to directly worry about it now. We just stick to 2 dimensions for a minute. Okay. So delta S multiplied by delta N. So let me start writing some of this down. Delta S is the side of the fluid element or particle along the streamline, and delta N is the side perpendicular to the streamline. Okay, side perpendicular to the streamline. And this little rectangle is at an arbitrary orientation, meaning whatever the local angle is, local tangent angle is. So if you draw a line as the tangent, the angle between the tangent and the horizontal is denoted as theta. So I'm going to denote, or I'm going to start annotating here. So this angle here, theta, okay, is the angle, is the angle between the tangent at the point at the center of the rectangle and the horizontal. And previously we talked about what is delta S and what is delta N, the sides of the rectangular element along the streamline and perpendicular to the streamline. Okay, let's deal with the easiest force first. What is the direction of gravity? Always vertically down, right? If we denote this to be horizontal, then we have to have the vertical. So gravity has to be along the vertical if this direction is the horizontal. So this is G. Okay. So if gravity, oh yeah, right here. So here's your depiction that relates to the direction of gravity in relation to delta S and delta N. The relation between the streamwise distance delta S and the angle and the vertical distance, the relation between the normal distance, the angle, and the vertical distance. Gravity is going to be vertically down, but if I want to do a force balance along 2 directions, one parallel to the streamline and one perpendicular to the streamline, how should I resolve gravity? if gravity acts along here, what would be the component that is along the normal and along the streamline? From this little two diagrams and using trigonometry, you can tell me. Gravity acts along delta Z. 73, are they trying to fry us here? Please look at this and tell me how to write delta Z in terms of angle and delta N. Delta Z equal to delta N cos theta or sin theta. And the component that is perpendicular to the streamline will be G cosine theta. Okay. Again, I'm skipping some steps. I'm just trying to summarize the key forces. So let me write here force components resolve. Gravity along the streamline is G sine theta G sine theta, and perpendicular to the streamline, or in other words, along the normal, is G cosine theta. I'm not going to make you do the full work of putting the equations together. I'm just going to ask you, this is G sine theta, the component along the streamline. Okay. What about pressure? What is the direction of pressure acting on this fluid element? How will you draw this? Of course, it's right here. You just have to interpret this for me. How will you draw the fluid pressure distribution around this rectangle? And I'm asking you that. I'm precisely asking you to do this. Let's say this is my streamline and I have my fluid element. Okay, this is delta S. This is delta N. And this angle is theta. I want you to draw the pressure distribution on this fluid element. This is the question. Actually, this is a good question for classroom or classroom part. Everybody has a sheet. So please draw this figure on your sheet and draw the pressure distribution around this rectangle for me. Yeah. Don't forget to put your name on it and take a picture if you want. Draw the pressure distribution around this fluid element. Point. I would be drawing, if I were you, trying to show the nature of compression or trying to show that pressure is compressive in nature. Did you have a question? Now, if I tell you the pressure at the center of this rectangle is P, okay? If the pressure at the center of this rectangle is P, answer this yes or no question for me. Is the pressure on this surface, is the pressure on this surface same as P or different from P? It would be different. That's your answer. Anybody else wants to say something? Would the pressure on the highlighted surface be same as the value at the center, or would it be different? Same. Okay. Can you tell me why you think it would be same?
Okay. So I'm answering this on the assumption that it is a
It's not a static fluid.
liquid.
It is a liquid, but it's not static. So why would you expect the pressure not to vary from point to point?
Yeah, it's not compressible.
That does not mean pressure doesn't vary. It just means the density doesn't change. Compressible or incompressible means density is decoupled from pressure. That doesn't mean pressure doesn't change anyway. Yeah, glad we got that clarified. So the pressure has to change from point to point because the fluid molecules are moving or the fluid particle is moving. And if the pressure is P here, and you know some calculus, how would you write the pressure at the station, which is at a distance of what? This distance is delta S divided by 2, right? If the entire side is delta S, then half of that should be delta S divided by 2. If the pressure at a point is P, how much is the pressure? Delta S divided by 2 units downstream. If the pressure at this point is P, how can you write the pressure at this section, which is this distance away from the point of interest? Fundamental calculus. I'm going to refresh you this. If the value of a function at a point x is y, what is the value of the function at a point which is slightly away from x? You know this. Taylor series. At least those in my numerical methods class, you have to say something. Okay.
I think I got it.
That's fine. So what you want to do is write the value of the function at a neighboring point is the value of the function at the point plus the rate at which the function changes along the x direction multiplied by the change in x value. This is the abbreviated or truncated Taylor series containing only the first derivative. Okay. Like asking this. We'll go back to our air vent example. Let's say the temperature here is 68 degrees. Okay. And I'm telling you the temperature increases by 1 degree Fahrenheit for every 2 feet. And if I move 4 feet, what temperature to expect? For every 2 feet, it's going to change 70. So for every 2 feet, it's going to increase by 1. So I moved 4 feet, which means the temperature should increase from 68 plus. Maybe if I write it in words, it will be clearer. Right. So I'm saying it increases by 1 degree Fahrenheit for every 2 feet. So if I move by 4 feet, you would say the temperature would be 68 plus 1 degree Fahrenheit over every 2 feet multiplied by 4 feet. This would give me 70 degrees Fahrenheit. Right? Are you able to connect with this very simple thinking? The value at a point multiplied plus the slope times the change in the value, change in x. Same logic, the value of the function at a neighboring point, let's say this is x, and the value of the function at x is y of x. And then I'm asking you to calculate what will be its value at x plus delta x. That would be this triangle. Okay, sorry, I have the ideas right, but I get my sketches wrong. Okay, just give me 1 second. All right, let's start over. All right. So I'm asking, this is my function. If this is x, okay, this is y of x. What is the value of the function at x plus delta x, which would be this triangle? What is this? What is the slope? What is the famous expression for the slope? First derivative, right? This is what you've been taught since your elementary calculus. Slope of a curve is given by its first derivative. So all I'm calculating is the value of this function y at x plus delta x is equal to whatever y of x is plus the change due to the slope and the delta x traveled. Suddenly I'm teaching numerical methods. Okay. All right. Now you tell me what will be the value of the expression for the pressure at this yellow or the highlighted surface. Yes, please. Exactly, which has a name. It's called pressure gradient. It's the rate at which pressure drops or changes along the streamline. Okay. So the pressure at this surface would be at the yellow surface. So the pressure at the yellow surface would be, like he said, P plus the pressure gradient multiplied by the distance, which is delta S divided by 2. I wouldn't talk so much if I had a little more few positive faces in the class. When I asked that question about what is the pressure here, all of you should see your faces. You are all like, is he talking Greek or Latin? So I had to assume that I have to explain more, and that's why I did. Okay, so for those who had this all along, my apologies, but for others, I had to talk more. Everybody is now seeing this. Everybody agrees with me that the pressure at a little distance down the road is the pressure at the point of interest where you know it, plus the pressure gradient times the distance. So quickly tell me, what will be the pressure at the other face? If the pressure here is the delta P over delta S, or partial derivative with respect to S times delta S by 2, what will be the pressure at this end? What will be the pressure at this end? So if this direction is positive, this has to be negative. So if this distance is delta S divided by 2, going backwards means you are going to a distance minus delta S over 2. Okay. So then this would be This would be P minus delta S, partial derivative with respect to S times delta S over 2. With me? Okay. I can make you do the same for the other direction. Instead of the pressure gradient along the streamline, you would be dealing with the pressure gradient normal to the streamline. Okay, let's not waste time on that. We have talked about gravity. Okay, I talked about gravity. I told you gravity has to be resolved along the streamline, and that contribution is G sine theta. Now, if you take this and I ask you what is the net force due to pressure along the streamline, what would be your answer? What is the net force on this fluid particle along the streamline due to pressure? It is not zero because this value and this value are not expected to be the same unless the pressure gradient is identically zero, which it is not. So it is not zero. What is it? How are you making that statement? So firstly, you can't just add or subtract pressures. You can only add or subtract forces. So first you have to think about what is the force on this yellow surface. Yellow surface is not just a line. You can assume it is a line multiplied by the distance that is coming out of the plane of the wave. So what is the force? So I'll say, let's do a calculation. The force along the streamline due to pressure. Look, the faster you answer this, we can skip to examples. So please tell me something so that I can, we can go from there. So what will be the force along the streamline due to pressure? At least tell me how you'll calculate. Yes. Pressure multiplied by area is force. Okay. So you have your element. Okay. At this surface, okay, we have the pressure P plus delta P over delta S times delta S over 2. And what is the area with which you should multiply? The area with which you should multiply, it would involve delta N times a width. I'll write width multiplied by delta N. Pressure times area gets you force. Okay. What will be the force on this face? P minus the pressure gradient, P minus pressure gradient times delta S divided by 2 times W delta N. W being the width that is coming outside. So this distance, the side of the rectangle is delta N. Now tell me what is the net force on this fluid element along the streamline due to pressure. I have two opposing forces. How will I compute the resultant? Subtracted. So if you consider this to be, if you consider this direction to be positive direction of S. Okay. What is the direction of this force? What is the direction of the compressive force on the left side and the right side? Both forces are like this. They are trying to compress the element. Okay. So this would be positive and this would be negative. Because this is along here and that's opposing. So you have to consider one positive, the other negative. Okay. So then the net force would be what? No, I'm trying to understand what the net force is so that I can equate it to the acceleration rate. There is an external force like gravity, there is pressure, and these two are causing the acceleration which we derived last lecture. Okay, we are not trying to do a static balance. Yeah, it's. Can you repeat that? Negative. No, negative. Okay, I'll just write because I'll arrive at the answer. W times delta N. Now this P will obviously cancel out. If you do the algebra, this P will cancel out. So what you're going to get is minus partial derivative with respect to S times delta S. Oh, sorry. I'll just type it, okay? So net force equal to minus partial. Okay. Take a minute. Tell me you are able to see where or how this is coming about. And I won't rush you. Where the two went? Good. Everybody has to tell me that they see this and they see how this last expression comes. All good? Everybody agrees? They're seeing this? Okay. So what I've done so far is this. Okay, let me write it in a clean sheet. We have considered along the streamline. Okay, we have considered the forces along the streamline. What are those forces? The component of gravity along the streamline is G sine theta. All right. And the component of pressure force along the streamline is, I can copy this and put it here, is Okay. This is what we have seen so far. Component of pressure force is this. Component of gravity is g sine theta. That looks odd. G sine theta is not a force. What is g sine theta? That's an acceleration. So to convert an acceleration into a force, what do you need to do? Multiply by the mass of the little fluid particle, right? And what is mass? What is mass? Density times volume. So we are going to multiply this by density, which is, we'll call it rho, okay? And then what is the volume of this little fluid particle? You look at this, it has a sides of delta S and delta N and a width that is W. So what is the volume? What is the volume of a cuboid? W times delta S times delta N, right? Multiply the three sides. That's your volume, right? So I'm going to take that and write, this should be equal to delta S times delta N times W. Okay, the term in the parenthesis obviously is your volume. Good. Good. If force is equal to, if Newton's second law, is F equals ma, what is A? What is the acceleration of this fluid particle along the streamwise direction or along the streamline? Can I say it is mass times the streamwise component of the acceleration? Can I say that? Yes. And streamwise component of the acceleration is what we painstakingly discussed last lecture. Okay. So I can write this is multiplied by, what is the streamwise component of the acceleration? I told you to think about it as the rate at which the quantity partial derivative with respect to, the quantity v squared over 2 changes along the streamline. Yes. Landing. Crash landing. Good. Are you able to agree with this? Okay. So now we need to do a force balance. This ma, this mass times acceleration, is the right side of F equals ma. And these two are the two forces that are on the left side. Okay. So I'm going to write this F equals ma. That's the title of this slide. Let me put that together. This is ma. Okay. This is ma. Mass times acceleration equal to this. And then sum of the forces equal to rho g sine theta times the volume, okay, minus partial derivative of pressure with respect to streamwise sequence of thought led you to first compute the forces along the streamline or streamwise direction and the acceleration along the streamwise direction, and then we are going to finally equate these two. Okay, we'll do that now. We'll do that now. So we are going to take this, put it here. This is equal to mass times acceleration, sorry, sum of the forces, which is here. So you should also write along a streamline, this relation is true. Along the streamline, this relation is true. Okay, so I can simplify this because this term seems to appear on both sides. On every term, the volume can be cancelled out of every term. So I'm going to get, oops. Okay. This is the force balance along a streamline. So I'm going to say this is the force balance along a streamline. Question for you. This is an expression that involves derivatives. Okay. Is it valid at a lot of points or is it written for a specific point? Okay. Any other responses? Sorry?
A lot.
Along a line?
A lot of points.
A lot of points. Okay. On the contrary, we did the entire derivation for a arbitrary point. Okay. We did this derivation for an arbitrary point, and this relation we derived is valid only at that point and its immediate neighborhood. It's not valid everywhere. Meaning, if you want to consider a small distance, a little bit away from the point of interest, yes, it can be considered valid, but it can't be considered for large distances. So what you need to think about is this picture has to be in your head whenever you see this relation. Okay, I'm going to take this picture. I'm going to put it here. And I'm going to add a note so that you actually remember this. Okay. So this relation, okay, this relation is valid at any point along a streamline. This picture or this relation is valid at any point along a streamline, but you have to write it for each point separately. It's not generalized for the entire curve or the entire streamline. If you want to do this, you have to zoom out. Instead of focusing on a single point, you should focus on an entire streamline, and we have to do that. What I'm saying is, you have a fluid flow. If you want to do this at a specific point, you write this relation. If you want to apply it for an entire streamline, then we need to integrate this over the entire streamline. Okay, I'll tell you what that means. Okay, so here is my streamline. Here is my streamline. Okay, let's say I start measuring distances from this point, which I'll call s equal to 0. And I'll consider an arbitrary point P whose coordinate is S, which is at a distance S from the starting point. With me so far? Okay. At P, you can write the relation which we got here. at any point P, you can write this relation. P can be any point. P can be here. I can draw P here. P is just a marker of an arbitrary point. And at that point, this relation is valid locally. Okay. If I want to have a relation that is valid for the over the entire streamline at every point on the streamline, what I would do is I'll first start with this picture. Oops. I'll start with this picture. Start with this picture. We would integrate the relation or the force balance at a point P over the entire streamline or curve. Please write this down. We are going to do this. It may not click immediately, but the more you think of it, it will work. I'm very sure. And in this era of instant gratification, some things don't click instantly. That's how it is. You have to, chew on it, and eventually it will come to you. Ready to move on? Are we okay? Yes. It'll be integrating over this curve, and I'll show you how that is done, like in a way that's not mathematically very dense. Okay. Okay. Is everybody okay? Can we move on? All right. So at this point, this relation is pretty generic. We just have said it is a fluid with density rho. We haven't told anything whether that density is a constant or incompressible, or that density could change with pressure. What's the big difference between a compressible and incompressible fluid? Please write that down on your sheet as part of your participation. I want you to write the key difference between incompressible and compressible fluid.
You said there's.
Sorry?
Statement.
I want you to write what you know as the key difference between incompressible and compressible fluid. You can tell me, it's not a quiz, it's just for participation. Just tell me what you think and we'll write down the correct thing. For an incompressible fluid, the pressure and density are independent of each other. Write that down. For an incompressible fluid, the pressure and density are independent of each other. For a compressible fluid, the density is a function of the pressure, or it depends on pressure. For an incompressible fluid, density is independent of pressure. That's the key difference, right? Look up, please. For an incompressible fluid, density doesn't depend on pressure, which means if I take this relation at any point, okay, I'll start with this relation. What can I do then? If density is just a constant, I'm going to do a little bit of an adjustment and write instead of writing it rho times this function, I'm going to call it 1/2 rho v squared 1/2 rho v squared, the derivative of 1/2 rho v squared equals rho g sine theta minus partial derivative of p over s. Okay, this is the relation that's valid at an arbitrary point p. Okay, now by integrating, what I'm going to do is I'm going to integrate this term by term. Okay, so I'm going to write again. These are the details that some books skip, and that's what puts us in all in it. It clouds up our understanding. So I'm trying to write it out. I'm going to integrate each term. Okay, this is equal to this times integral rho g sine theta, okay, equal minus integral the partial derivative of p with respect to s ds. This is what integration means, right? I'm counting on your calculus knowledge. Integrating along the streamline with respect to s. Good with me? Are you okay? So are you supporting your head with 13? Just kidding. Okay. So if you were to integrate this, how would you go about it? You are all taken calculus, right? How do you do integration? With respect to the parameter s. What is s? S is the distance measured along the streamline. Okay. So if I want to do the integration, I would pick 2 points. Let me call them A, where the distance is SA, and B, where the distance is SB. Okay. I'll pick 2 specific points whose streamline coordinates are SA and SB, and I would do the integration between those 2 points. Okay, I would do the integration between those 2 points. So I'm going to take this and say integrating between A and B. A is at a distance of SA, and B, which is at a distance of SB. So then I would take this integral. It's between 2 specific points. So I'm going to write this is, okay, I'm going to write, if I integrate this between 2 specific points, how will this look like? What will be the value of the each terms? What will be the value of each of the terms? This is the derivative with respect to s times ds. So this is like writing, anyone? This is like writing half rho v squared, half rho v squared at the coordinate SB, 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 SB minus what? Left hand side. Just think about left hand side. I am integrating it between SB and SK, 2 distances. The quantity half rho v squared evaluated at SB minus, I know you know it, evaluated at SA. Okay, this symbol means evaluated at SB and evaluated at SA. Oops. So evaluated at SA. Okay. What will be the second term? That will be rho and g, they don't change with sine theta. Sorry, they don't change with with s. Okay, so that will be integral. What's remaining is integral sine theta ds except we have to evaluate this between SA and SB. SA and SB. Okay, and what will be this term, the last term? That will be the pressure at SB, the pressure at SB minus the pressure at SA. Okay, and I have to put this entire thing in parenthesis so that the sign is preserved. What have we done? Integrated each term between two finite points. Between two finite points. Okay. With me so far? Yes. It's too simple. That's a yes. Okay. Not too hard. Good. I like to hear. Okay. So this angle is a pesky parameter. Like this is like knowing the local slope, and we don't want to do that. Okay. We want to get rid of the angle and write it in terms of something that's easier to think about. Okay. If you think about this curve here, A, the point, is defined by its streamwise coordinate SA, and B is defined by SB. But A and B are also at different, they could be at different elevations, meaning with respect to height, Z coordinate, they can have a coordinate which is related to ZA and ZB. Okay. If you go back to one important picture here, if you go back to this picture here, I don't know how much this is visible. Look at this picture. Along the streamline, the relationship between the angles. Sorry. Look at this bottom figure. The relationship between height and distance along the streamline, which you can relate as sine theta equals delta Z divided by delta S. Yes, trigonometry, right? So you can write delta Z equals, delta Z equals delta S sine theta. Can you write that? Delta Z equals delta S sine times sine theta. So I'm going to take this, go back here. Go back here. Copy this picture. I don't need the entire picture. I just need a small portion so I can crop everything else. And then make this bigger. Still crop it some more. Okay, good. So I have this figure here. Okay. So I'm going to write sine theta ds. Okay. Sine theta ds is nothing but dz. Can I write that? Like a finite small distance. I'm turning that into a differential. Delta ds and dz. So I can replace the integration variable. So I can take this. And instead of this, I can write this is equal to this is equal to dz, and the limits will be za and zb. How about that? Integral of dz from za to zb between points a and b, or in other words, this integral is equal to d. How do you physically, or in words, how will you say zb minus za if z is the vertical coordinate? I know, say it. Change in height or change in elevation. If you have a streamline, you pick 2 points. This integral is basically the elevation difference between them. Okay, so this is nothing but zb minus za. So the only thing that had still an ugly integral is now going to be replaced by a elevation change. zb minus za is nothing but elevation change. Elevation change. Okay, so then we are now one step closer to the famous Bernoulli equation. I'm going to write that here. And now Bernoulli equation. That would be I'm going to replace this with ZB minus ZA. So this equation, as we did so far, is applicable between 2 points A and B along the same streamline, or I should just say in plain English, along a streamline. But the reason I say same streamline is people sometimes forget that, or I'll just say along a streamline. As long as they are on the same streamline, we are okay. Yes.
So integrating balance equation, determining the pressure.
Yes. Yes, we now have a relation between the local velocity at B, the local velocity and the local pressure and the local elevation. That's what Bernoulli equation is about. It's a relation between local velocity, or I should say local speed, pressure, and elevation or height between 2 points on a streamline. And this is the basis of many measurement methods as well as analysis methods. Okay, and we'll see those as examples. One of the important assumptions we did here so far is that we did assume the fluid is incompressible. Okay, but that can be easily changed by starting over with the equation of state for the fluid that connects pressure P and density rho. What would that equation of state be? Maybe can you give me an example? What is an example of an equation of state? What is a relation that famously connects pressure and density for fluid, maybe like a gas?
Yeah.
Ideal gas law is what I am kind of referring to as generally equation of state, because ideal gas law is an equation of state. It's not the only equation of state. There are other possible equations of state. Okay. As far as our course is concerned, this equation is what we will use for problem solving involving incompressible fluids. And it remains to be seen if I will have time to go into compressible fluids, but this is definitely going to be, we'll do examples. Okay. So in page, in section 3.2, Dr. Hochstein, who is one of the authors of this book, says this is the celebrated Bernoulli equation. That's his word, the celebrated Bernoulli equation. Okay. Sometimes it is also written as, now 1 minute, then I'll let you write. I just said that I'm picking 2 points, A and B, right? I didn't exactly say which 2 points, or I didn't place any constraint. We can apply this Bernoulli equation between any 2 points as long as they are on the streamline. So we can just say, we can just take this equation and state it differently. We can also say the quantity half half rho v squared plus pressure, half rho v squared plus pressure plus rho gz equal to a constant. And this is true also for between any 2 points. So this is just another way of writing Bernoulli equation. You can write it between 2 points if you know their coordinates, or you can in general say the sum of the half rho v squared plus pressure plus rho gc is a constant for the entire streamline, meaning you can take any 2 points and this constant will add up to be the same. And we'll see how to use it in problems. Okay. And last point, we started by doing a force balance, correct? What is the unit of this, each term in this equation? Can you check and tell me? What is the unit? Half rho v squared, pressure, rho gc. What is the unit of all of each of them? Firstly, they all have to have the same units. Right? They are all, we are adding them up, literally adding apples and oranges if they don't have the same units. So what is that unit? It should be the unit of pressure, which is pascals. Right? Pascals. Okay. Here's a trick. The unit of the terms is Pascal, which is what? Newtons per meter squared. That's what you always know, newtons per meter squared. But if I do a little trickery and say Newton per meter squared is nothing but Newton meter per meter cube. Can I do that? Newton meter per meter cube. Is that okay? Right? Should be okay. And what is Newton meter? Do you recognize? What is force times distance? Work. And work and energy are equivalent. So we can write this is joule per meter cube. Keep doing this. Joule per meter cube. Okay. So the same equation that I write here, if I take this, I mean, I'll treat both of them to be interchangeable. So if I write that here, okay, same equation can also be interpreted as the energy density at that point. Energy density. How do you interpret energy density? The same equation can also be considered as the energy density at a point. Energy contained by the fluid per unit volume. And that energy is due to three causes. The first cause is due to motion, which is why we would call it fluid kinetic energy. Okay, so let's write this down. Okay, are you done up to here? Can I continue? Okay, so I'm going to write this here. Half rho v squared, okay, is the energy due to motion. Okay, it's the kinetic energy per unit volume, and we give it a name, dynamic pressure. We give it a name, dynamic pressure. Okay, we are going to start, we are not going to keep calling it half rho v squared anymore. Henceforth, it is dynamic pressure. It's the pressure that arises due to the fluid's motion. Okay. The quantity P is the energy due to molecular motion of the fluid molecules, or I should say microscopic motion of the fluid molecules, which you can't see but can only sense, which can't be seen by the unassisted eye, but can only be sensed. Okay, but can only be sensed. It is the thermal energy per unit volume. Thermal energy per unit volume. We give it a name. Henceforth, it is called static pressure. Static pressure. No more calling it just pressure, because pressure itself is an umbrella term. We are going to call it static pressure. It is defined by the thermodynamics of the fluid. It could be incompressible, meaning pressure. I mean, you know this, but I like to say it. Pressure and density are independent. It could be compressible, where pressure and density are related through the equation of state. Okay. And you're going to assist me with the last type of last term, which is rho g times z. What is that? Do you recognize? Can you comment? It is the potential energy per unit volume arising due to gravity. So it's potential energy itself is, it can be due to a spring or it can be due to any force. This is due to gravity. So it's gravitational potential energy per unit volume. Just 1 second here. Nice answer. So rho g times z is the energy due to gravitational force. It is a potential energy due to the relative position of the point in a gravitational field. Okay, it is the P per unit volume. We give it a name. Okay, I'll change the font size. My apologies. We give it a name. What's the name? Pressure head. The word head is used because it's usually used to denote elevation. Okay. There are other terms too. I'm not able to exactly remember all of them, but as it comes up, I'll tell you. But pressure head is a commonly used term. Okay. So there is dynamic pressure, static pressure, and pressure head. All right. Questions before we move on? Yes. Yeah, it is due to the height. The word head is used to denote height in it's a little bit of historical thing. Somehow pressure head plumbers understood fluid mechanics better than mathematicians. So that name stuck. And then the mathematicians caught on. Okay. Now, can we consider some limiting cases, like some special cases which are easy to reason and will bring back what happens when you have a static fluid? That is, you studied fluid statics through all of last chapter, right? Can we recover the key result from that chapter from this equation? What happens in a static fluid? What is the first thing we should do? There is no motion, meaning V is 0. Right? First term is 0, which gets you to P plus rho Gz is equal to constant. Now, it's easy to forget that this should be along a streamline, not perpendicular. What does that mean? Sorry? So if I have a tank, if I have a tank, I take a point and let's say I draw a streamline that is flat between any 2 points on the streamline. P plus rho Gc is a constant, meaning if it is at the same height, the pressure has to be constant. It of course doesn't apply in the transverse direction because if you're traveling in height, you are jumping from streamlines. So you can apply this along the horizontal, but not along the vertical. Okay. Okay. Let's consider one more example. Okay, one more like limiting case. No elevation change, but there is fluid motion signified by the speed v. If you have no elevation change, what does that mean? How will this equation modify? There is no, you're going to consider 2 points. Okay, so let me draw it like here. I'm going to draw a streamline where I'm considering 2 points, but the elevation of these 2 points are one and the same, meaning let's say I consider 2 points A and B. ZB is equal to ZA. which tells me I can take this equation and just drop this term and have the remainder. Okay. Right? I can do that, right? Although this is a little bit out of schedule, I'm going to say this nevertheless. How many of you have done a pressure measurement in some laboratory course, or at least in other contexts? Have you used any what is called as a pitot tube? Pitot tube? No? Yes?
General aviation.
General aviation. Thank you. So what can you recall something?
And the fluid, it's much the instruments would compare the pressure in the static air inside the airplane to the outside air.
Do you know how it is done?
But no, I don't know the.
Okay, you are a aviator. Now you are going to become an engineer. Let's learn it. Yeah. So it's a little bit out of turn, but I'm going to still say it. So a pitot tube looks something like this. Okay, pitot tube. It has a tube. Okay. It also has a sheath or a sleeve. And a hole that is drilled here. Okay. So these two tubes are disconnected. They are okay. A fluid, that is, if in your case, a pitot tube that is mounted outside the aircraft is going to read the total pressure, the dynamic pressure as well as the static pressure, and I tell you how. The pitot tube that is installed inside your aircraft is just reading the cabin pressure. Okay. So what happens is this: as fluid comes through here, okay, the fluid motion, let's consider, is directed along this direction or this arrow. The fluid with its kinetic energy is entering the inner tube. Okay, it's entering the inner tube. On the outer, the fluid is flowing. Let's assume that this is still V. Okay. When the fluid molecules are flowing with a velocity V in this direction, what do you think happens in the transverse direction? The transverse direction, are the molecules moving? If so, with what velocity? That is the fluid molecules. If I take a little volume here, I have 1 minute. Let me see how well I can do this. Let's see, I take a volume here. When I say the fluid in this little volume is moving with a velocity V, what is the implication? It means all the molecules are moving with V, but they also have their little random velocity due to molecular motion. Okay. Same goes here. Same goes here, and same goes here. In the transverse direction, the molecules do have a velocity, and they do enter this outer sleeve with that thermal velocity or with that molecular velocity. So the pressure that you sense in the inner tube is the sum of the static and the dynamic, whereas the pressure that you sense in the coaxial outer tube is only the static. So what you get here, what you get in here is P plus half rho V squared, whereas what you get here is only P. So if I tell you the P plus half rho V squared is sensed in this limb and only the static pressure is sensed in this limb, if you are able to measure the pressure difference between these two, can't you say what is the dynamic pressure? So the difference between these two, over here, This is P plus half rho V squared. Over here, it's only P, which means the difference between them is the dynamic pressure. So if you can measure that pressure difference, you are essentially measuring the fluid velocity. And that's how your indicator is showing so many knots per feet or whatever, knots per second or something. This is the measurement with a pitot tube, which uses Bernoulli equation in a sense that the streamline between this between this point and this point, they apply the Bernoulli equation to derive the half rho V squared. This is one of the most common applications of Bernoulli equation. Okay. So we are wrapping up that all that the theory and the concept talk. Next lecture, my hope is to do examples related to this topic. And what is the date of the next lecture? That is 17th. Whatever I do until end of next lecture is what is going to be on your test on the 24th. What I do on 19th will not be on the test, but will be on the comprehensive exam. Understood? So be present for next lecture. We're going to do examples and start doing problems on chapter 2. And please give me your sheets so I can mark attendance. Thank you.